Okay, so like I said last time, today we're going to cover chapter 4, which is on polynomials, and then we're going to start talking about some things in chapter 5, but we'll start in 5b, and then we'll go back to 5a. Okay, so chapter 4 in your textbook is on properties of polynomials, done starting from the very basic definitions, covering all the fundamental facts, and showing all the details. Okay, but of course, polynomials are not linear algebra. So I won't go into all the details that your book does, but it's good that all the details are there if you want to, brush up on polynomials. I'm just going to cover some of the facts that we need, basically. So first theorem is called the division algorithm. As follows. So given polynomials, let's say P and S, so these are polynomials in one variable with coefficients in F, and S is non-zero, then there exist unique polynomials Q and R such that P is equal to QS plus R, and the degree of R is less than the degree of S. Okay, so this says that you can divide the polynomial P by the polynomial S, and this Q is the quotient. Right, so like Q times S is kind of like P, except that potentially there's a remainder. That's what the Q and the R stand for. Okay, so in Math 300, you learned the division algorithm for integers. Given any two integers, P and S, you can divide P by S, right? Some multiple of S, Q times S, is within a very small remainder of P. How small? Well, R would be less than S in that case, right? So in the integer version, the thing that you have is that you have R is less than S, right? The remainder is smaller than the thing you divided by. But for the polynomial version, our notion of size is degree. So what you could get is you can divide P by S, and the remainder you get has a smaller degree than S. Okay, so which means that I need some convention for degree of 0 and degree of linear polynomials. So by convention, the degree of the 0 polynomial is minus infinity. So basically it has a smaller degree than every polynomial. Okay, so let's just see an example. Right, so let's suppose that P is a polynomial 2x cubed plus 3x squared minus x plus 1, let's say. And let's let S equal x minus 1. Okay, so you learned in pre-calculus or calculus how to do long division of polynomials, and this long division algorithm will give you the quotient and the remainder that are guaranteed by this theorem, right? So the way you learn to do it is you learn to write, well, I guess I don't know how you learned how to do it. This is how I learned how to do it. Right, it's just like when you divide integers, you write the thing that you're dividing underneath the bar, the thing that you're dividing by to the left, and then there's like a x cubed place, an x squared place, an x place, and a x to the 0 place, essentially. So to get 2x cubed, you need to multiply by 2x squared. That gives you 2x cubed minus 2x squared. Right, then you subtract. So here you get 5x squared minus x. To get 5x squared, you need to add 5x here. Now you get 5x squared minus 5x. You subtract again, and you get 4x plus 1. So you get a plus 4 here. 4x minus 4, you subtract again, you have a remainder of 5. And you know that you've gotten the remainder once the degree of R is less than the degree of S, right? So here S has degree 1, this remainder has degree 0. So this says that 2x cubed plus 3x squared minus x plus 1 is equal to 2x squared plus 5x plus 4, that's q, times x minus 1, that's s, plus 5, that's the remainder. So this is p, this is q, this is s, this is r. And as you can see, the remainder has a smaller degree than the thing you divided by. Okay, so we should prove this. I mean, essentially the proof, so you actually can do a proof that's very similar to the proof that you did in Math 300 for integers, if you remember it, where you use degree instead of absolute value of integer, which is what you do in the integer case. But we can also prove this using some concepts from linear algebra. Here's the proof. Okay, so let's let degree of p, let's give this a name, say it's n, and degree of s, let's call this m. Okay, now if n is less than m, right? So here it's like this, you're dividing a smaller polynomial by a bigger polynomial. Then if you have p equals qs plus r, well, this one has smaller degree than this one, which must mean that q is 0, right? This must be 0 because otherwise q times s would have too large a degree, right? So this implies that q equals 0. So p equals r. That's your only choice for what r is. Since all this is forced, these are the unique polynomials that satisfy the property, right? P equals 0 times s plus p. This is just like when you divide a smaller number by a bigger number, right? If you divide 3 by 8, well, 3 is equal to 0 times 8 plus 3. It has a quotient of 0 and a remainder of 3. Okay, so that's sort of the trivial case. So let's suppose that n has degree bigger than or equal to m. And now we're going to do something a little clever. Let's define a linear map. Call it T, and it's going to go from polynomials of degree n minus m cross polynomials of degree m minus 1 to polynomials of degree n. Okay, and what is T going to do? It's going to send a pair of polynomials qr to qs plus r. Okay, so s has degree m. So if you take a polynomial of degree less than or equal to n minus m, that's what the q is coming from, then this thing will have degree less than or equal to n. And r is coming from polynomials of degrees less than or equal to m minus 1, which is also of degree less than or equal to n. So this polynomial definitely has degree less than or equal to n. If q comes from polynomials of degree less than or equal to n minus 1, r comes from polynomials of degree less than or equal to m minus 1, and s is a polynomial of degree m. Okay, so you should check that T is linear. In other words, if you have Q, I guess I should just write what you should check. If you have Q0, R0 plus Q1, R1, it's the same thing as T of Q0 plus Q1, R0 plus R1. Okay, this just follows from properties of multiplication and addition of polynomials. Okay, but in fact, this T is actually an isomorphism. So claim T is an isomorphism. So why is this? Well, in order to show that something's an isomorphism, I need to show that it's injective and surjective, right? Of course, if these two vector spaces have the same dimension, then it's enough to show that it's either just surjective or just injective. Okay, and we'll see in a second that these have the same dimension. But let's actually show that it's injective. So why? Let's suppose that QR is in the null space of T. Then what this means is that QS plus R equals 0. Okay, but what would it mean if QS plus R equals 0? Again, remember, this polynomial has degree m, exactly m, and this polynomial has degree less than or equal to m minus 1. Right, because it comes from here. But if you have a polynomial of degree m and you multiply it by something, and then add a polynomial of degree less than or equal to m minus 1, you can never get 0, right? Because, well, you can almost never get 0. This thing will have degree at least as big as m most of the time. And so you can never get 0 because R will never be able to cancel out a polynomial of degree bigger than or equal to m, unless Q equals 0. Right, so this is impossible unless Q equals 0. That means that Q equals 0, which also forces R to equal 0. Right, but this means that the only thing in the null space of T is the 0 vector 0, 0. So the null space of T is trivial, which means that T is injective. Okay, and now we just need to consider the dimensions of the things involved. So let's talk about the dimension of this side. This is the product of two vector spaces, so the dimension is the sum of the dimensions. Right, so what is the dimension of the left-hand side? It's a dimension of Pn minus mf. This one has dimension n minus m plus 1, plus the dimension of polynomials of degree less than or equal to m minus 1. That one has dimension m. And this one has dimension n plus 1. So these two sides have the same dimension. So we have an injective map between two spaces of the same dimension. That means that T actually is an isomorphism. Since dimension of the domain equals dimension of the codomain. Right, which means exactly that for every polynomial in here, there's one and only one Q and R that maps over to it under T. In other words, for every single P in this side, there's exactly one Q and R such that P equals QS plus R. So proving that this is an isomorphism actually proves the theorem. Okay, so this is a division algorithm for polynomials. Okay, but again, the main thing, I mean, so there are parts of this proof that are linear algebra, right? So the idea of an isomorphism, the idea that two vector spaces of the same dimension, to show that they're isomorphic, you can prove that there's just an injective linear map from one to the other, or just a surjective linear map from one to the other. But the statement of the theorem is not a linear algebra theorem. It's a polynomial theorem. So it's more important to know the statement of the theorem and how to divide polynomials. Okay, we also have a very important theorem called the fundamental theorem of linear algebra. Sorry, the fundamental theorem of algebra. Okay, which I'm an algebraist. I do algebra for a living. I don't really think of the fundamental theorem of algebra as an algebra theorem. It's really sort of an analytic fact, actually. And in fact, every proof of the fundamental theorem of algebra uses some analysis. On the other hand, some of the roots of algebra are related to this. Let's just state it anyway. What I'm trying to say is I don't know if I love the name of this theorem, but this is the common name of the theorem. Let P be any polynomial with coefficients in C in one variable. Well, let's let it be a non-constant polynomial. Right, so degree at least 1. Then what the fundamental theorem of algebra says is that every non-constant polynomial with coefficients in C has a root. There exists lambda in C such that P of lambda equals 0, i.e., every non-constant polynomial has a complex root. Okay, so this is a very non-trivial theorem. Right? For example, it's not true over every field. It's not true over R. Right? Because we know that this is not true over R. Well, what I mean to say is the complete analog isn't true over R. In other words, not every real polynomial has a real root. Right? X squared plus 1 does not have a real root. But if you view it as a polynomial over C, it does have complex roots, right? So it doesn't violate the theorem. But if you like ask for this property except happening entirely over R, it would be false. Okay, so like I said, the proof uses, every proof uses some analysis facts. But let me just state the corollary, which you could also, this corollary is also sometimes called the fundamental theorem of algebra. It's this: given a polynomial of degree D greater than 0, so a non-constant polynomial, there exists constants C lambda 1 up through lambda D such that P of Z is equal to C times Z minus lambda 1 times Z minus lambda 2 ... Z minus lambda D. So these lambdas are the roots of P. Okay, so what this is saying is that every polynomial over the complex numbers you can completely factor. Right? You've taken the polynomial and you've written it as a product of D linear factors times some constant, right? Because the coefficient at the front might not be 1. You can completely factor every polynomial over C. Okay, and if you accept the theorem, the fundamental theorem of algebra, then the corollary is reasonable to prove. So first of all, the result is clear if degree of P is less than or equal to 1, which I guess it's just equal to 1 in that case, right? Because we assume that D was greater than 0. Right? Because if so, then every linear polynomial looks like alpha z plus beta for some alpha and beta, which means that you can write it as alpha times z plus beta over alpha. Right here, alpha is non-zero because I said that the polynomial had degree 1. So this is c, and this is negative lambda 1. So you can, of course, factor linear polynomials, can just pull out the scalar. Okay, well, now suppose that p has larger degree, bigger than or equal to 2. Now, by the fundamental theorem of algebra, p has a root, a complex root. Call it lambda 1. Now, we use the division algorithm. So by the division algorithm, I can divide p by z minus lambda 1. So p is equal to z minus lambda 1. There's some quotient, and there's some remainder. Okay, but the degree of r should be less than the thing that you're dividing by. Right, so with degree of r less than degree of z minus lambda 1, which is 1, which means that r is a constant polynomial. Okay, but now if you plug in lambda 1 into both sides, you get p of lambda 1 equals lambda 1 minus lambda 1 times q of lambda 1 plus r of lambda 1. R is a constant though. This is 0, this is 0. That means that this is 0. So r is a constant polynomial that equals 0, which means that r equals 0. In other words, if lambda 1 is a root of p, then you can factor it out. Right, so now p of z is just z minus lambda 1 times q of z. Now you use induction. So you factor out one root. Now you have a smaller degree polynomial q. You can factor a root out of that. That gives you another linear factor, and then you keep on going until q is linear. Well, once q is linear, you can factor out the constant, and that gives you the claimed factorization. Okay, so once you know that every polynomial has a root, you just divide them out one at a time to show that over C, every polynomial can be completely factored into linear factors. Okay, and I guess I didn't prove this, but this factorization is unique up to reordering the factors. Okay, so this is sort of just like the fact that you can factor every integer as a product of prime factors, which is unique up to reordering. Same idea. Here, the polynomial can be written as a product of linear factors. The factorization is unique up to reordering. Okay, so now we'll jump into 5b and talk about the section called Polynomials Applied to Operators. Because this is how one of the ways that we're going to use polynomials in this class. We're going to apply them to operators. Okay, so normally what we're used to doing is we're used to applying polynomials to numbers. Right? So normally, we apply polynomials to numbers. Or even to points in Rn, maybe, if it's in more than one variable, right? But if like P of z equals z squared minus 1, that's a nice polynomial living in the set of all polynomials. What we're used to doing is we're used to saying, oh, well then P of 2 equals 4 minus 1 equals 3. It's like you've applied the polynomial z squared minus 1 to the number 2. You've plugged in a number into the polynomial. It turns out that it will also make sense to take a polynomial and plug in an operator. And this will be kind of an important concept. So in order to do this, right, so what I'm going to do is I'm going to take polynomials like this, and then I'm going to plug in an operator like P of t to get like t squared minus 1. But there's sort of two issues here, right? One is, what is t squared if t is an operator? I think I want it to be an operator. And then the second thing is, what is minus 1 in this context? So that's what the following definition is supposed to. So suppose that t is an operator. So remember, an operator is just a linear map from a vector space to itself. And let's suppose that m is a positive integer. So we'll make several definitions here. So first, we'll define t to the m. So I'm going to tell you what I mean by t squared or t cubed or whatever. What this means is t composed with itself m times. Right, so this makes sense because t is an operator. Right, t goes from v to v, which means that once you've applied t, you're still in v, you can apply t again. Right, for a general linear map, totally general linear map from v to w, it makes no sense to take a power of it. Because once you've gone from v to w, you can't apply the same linear map because you're in a different vector space. But if t is an operator, t goes from v to v, you could apply t again and apply t again. So for an operator, it makes sense to define a power of the operator. Okay, so for an operator, you can take a power. So t to, what is t to the 0 now? T to the 0 should be something like 1. Of course, we want it to be an operator, which means that we should take the identity operator. So t to the 0 is defined to be the identity operator on v. Okay, and if t is invertible, not every operator is invertible, but if it is invertible, then we define t to the minus m to be t inverse to the mth power. Okay, so this is only defined if t is invertible, but if t is invertible, then also you can take negative powers. Okay, and this exponent taking powers of an operator behaves nicely. So if t is an operator, then if you have t to the m composed with t to the n, well, this just means you do, this means you do tm times, this means you do tn times. So this operator is the same thing as doing tm plus n times. Okay, and if you have t to the m, that's an operator, you can take it to the nth power. Right, so this operator says take tm times. This operator says take whatever's in the parentheses n times. So altogether you'll have t done mn times. Okay, so this notion of taking the power of an operator is well behaved in the sense that the exponents behave the way we expect them to. Which means that we'll be able to substitute operators into polynomials because there's a well-defined notion of taking the exponent. So that's this definition. So suppose that T is an operator on V and P is a polynomial. And let's be very specific. Let's suppose that P of Z is A naught plus A1Z up through AM Z to the M for some scalars. Okay, then I'm going to define what I mean to plug an operator into a polynomial. So then P of T, this is an operator. So this is the operator defined by P of T equals, well, A naught is just a scalar. That's not an operator. So we should take A naught times the identity operator. That's what the A naught is going to correspond to. Plus A1T plus A2T squared plus AM T to the M. Okay, so since T is an operator, all of its powers are defined. Those are operators. If you scale and multiply, you again get an operator. You add, you again get an operator. So this whole thing is an operator. Okay, so example. Let's let D be the differentiation operator on a set of polynomials, right? This is our favorite example of an operator. Right, so what D does is it returns the derivative of the polynomial Q. Okay, now let's take just some polynomial to plug this operator into. So let's let P be the polynomial, let's say 3 plus 2x squared minus x cubed. So now I have an operator and I have a polynomial. Let me plug my operator into my polynomial. So P of D is defined to be 3i plus 2d squared minus d cubed. This is a new operator. What does it do to a polynomial? So if I apply P of D to Q, that applies the operator 3i plus 2d squared minus d cubed to Q. The identity operator on Q just returns Q, so this gives you 3Q plus the d squared operator differentiates twice, so 2Q double prime minus Q triple prime. This is true for this is what it does to any polynomial. It returns 3 times the polynomial plus 2 times its second derivative minus its third derivative. Again, this makes sense because when you've taken the derivative of a polynomial, you again get a polynomial. So you can take its derivative again. Okay. So let's think about some properties. Whoops. Let's think about some properties of this thing. Oops, okay. Here's the proposition. Suppose that P and Q are two polynomials, and T is an operator on some vector space V, then two things are true. So one is that PQ of T equals P of T Q of T. And the second thing that's true is that P of T Q of T equals Q of T P of T. Okay, so these two parts are saying actually quite different things. What does the first one say? The first one says, well, if you have two polynomials, you can multiply the polynomials together. That gives you a new polynomial. And you can plug in t. That gives you an operator. That's the left-hand side. Multiply the polynomials and then plug in t. The other side says you can plug t into p, you can plug t into q, and then you can compose them. That also gives you an operator. That's this side. So this says that like the product of polynomials, when you apply it to an operator, corresponds to composing the two operators. What does the bottom one say? The bottom one says, okay, well, if you first do q of t, that's an operator, and then you do p of t, it's the same thing as first doing p of t and then doing q of t. Right? So these are just composing these two operators in the opposite order. Okay, but remember that in general, when you compose two operators, the order matters. In general, function composition is not commutative. This says that in the special case that the two operators that you want to commute are polynomials in a single operator t, then the order in which you compose does not matter. But in general, the order will matter. Okay, so this is going to use strongly that these are the two operators you're talking about, p of t and q of t, are operators that are polynomials in a single operator t. Okay, but let's just note that one will imply two. Right, so if we had one, then we know that if you take two polynomials, the order in which you multiply the polynomial doesn't matter. Right, so these two are the same polynomial. Right, then if part one is true, pq of t, that's p of t, q of t by part one. But we know that's qp of t, which would be q of t, p of t. So if part one is true, then part two is automatically true. So it suffices to prove one. Okay, but one is just, again, one of these exercises in notation and definitions. So to show one, we need to write these polynomials. So let's say that p is, say, the sum j equals 0 to m of a j z to the j. So it's some polynomial like this. And q is some sum k equals 0 to n bk q to the z to the k. Okay, then the product, how do you multiply these two polynomials? You take it, well, it's just a double sum, j equals 0 to m, k equals 0 to n, aj bk, z to the j plus k. This is just the formula for how you multiply two polynomials together. Essentially, you just do it term by term. Okay. This means that if you take, well, let's take p of t times q of t. P of t is you plug t into this into p. Q of t means you plug t into this operator. Sorry, you plug this operator t into this polynomial q. Okay, but now we use the fact that composition of operators that are powers, right? We proved that t to the m times, or we said that t to the m times t to the n is t to the m plus n. Also, since t is linear, you can pull scalars through an operator. So in the end, if you think hard about what this means, you'll just get a, j, b, k, t to the j plus k. And this is the same thing as plugging the operator t into the product of polynomials pq. Okay, so just an exercise in notation. The point is that basically the product and sum of the operator t and the powers of the operator t basically behave just like the product and sum of the powers of the variable z. That's the whole point. So if you multiply the polynomials, it's the same thing as composing the two operators. Okay, so kind of just a technical proof, but the result just means that this process of applying polynomials to operators just behaves very nicely. When you write something down, the thing that you hope to be true is true. Okay, now, why are we going to want to do this? For many reasons. But in 5a, we're going to see some use of this when we study eigenvalues, eigenvectors, and invariant subspaces. Okay, so your book has a nice little introduction to chapter 5, or section 5a. And let me just go through that in the last bit of today's lecture. Okay, so suppose you want to study an operator t. It's on a vector space V. Also suppose that you can break V up as a direct sum. So suppose that V is U1 plus U2. Right, so if you want to study an operator T on a vector space V, and you can break up the vector space V into a bunch of smaller subspaces, then to understand T, you just need to understand what it does to every one of these little subspaces. So to understand T on V, you need to understand T on each uj. In other words, you only need to understand the restriction to every uj, right? Because every vector in V will live in one of these u's, one and only one of these u's. That's what it means to be a direct sum. If you want to understand what T does to any vector in V, it's enough to know what T does to any vector in any of the u's. So you just need to study the restriction. T restricted to uj for each j. So if you can break up the vector space, then you can study something smaller, just what T does on each of these smaller subspaces. Okay, so that's good because the restriction is defined on a smaller vector space. So it should be easier to understand. Right, so uj is smaller than V. So T restricted to uj should be easier to understand. However, what is the restriction? Okay, so but the restriction to uj is a linear map from uj to V, right? Because what T is an operator from V to V. You plug in a vector in V, it spits out a vector in V. If you plug in a vector in U1, it will just give you a vector in V. What you're not guaranteed is you're not guaranteed that T takes a vector in U1 and maps to a vector in U1, right? T could basically do anything. So not necessarily, it's not necessarily true that T maps Uj to itself, because it could map something in U1 to something in U2, right? That would still be okay for an operator on V. In other words, this restriction is not necessarily an operator. Right, so breaking up the vector space V into a direct sum of smaller vector spaces makes things easier because you're dealing with a linear map defined on a smaller vector space, but could make it worse in that you're no longer getting operators on each of these smaller vector spaces. So for example, you lose the ability to take powers, right? Because I can't take the power of this restricted operator because its codomain is V. Now I can't plug that into T restricted to Uj. So what would be very nice, it would be nice if T restricted to Uj is actually an operator from Uj to Uj. In other words, what we are naturally led to want to study is subspaces of V that are preserved by the operator T. Because then when you restrict to that subspace, you'll get an operator on that subspace. So this is the first definition of the chapter. Suppose that T is an operator on V. A subspace U of V is called invariant under T if U in U implies that TU is in U. It's exactly the condition that I wanted above. When you plug in something from the subspace, the output is also in the subspace. So if you just restrict to the subspace, you will get an operator on the subspace. In other words, T restricted to U is an operator on U. Okay, so let me give you maybe some example, gratuitous example. Let's let V be R2. Okay, and let's define, so in order to find an operator, I just need to tell you what it does to a basis. So we have the standard basis, E1, E2. So let's suppose that T is an operator on R2, given by like what T does to E1 is it sends it to like 2, 0. And what T does to E2 is it sends it to 1, 1. This is a perfectly fine operator, right? It has matrix. If with respect to the standard basis, it has this matrix. But what we can do is we can break up V into a direct sum of two subspaces, right? So I can let U1 be the span of 1, 0, which is just the x-axis. There's U1. There's U1. And I can let U2, say, be the span of the second basis vector. There's U2. In this case, V is U1 direct sum U2. Every vector can be written uniquely as something in U1 plus something in U2. But these two subspaces behave differently with respect to T. right? So T is an operator on R2. If you restrict T to U1, T restricted to U1, what happens? Well, if you plug in a vector in U1, a vector in U1 is something on the x-axis. So you plug in like an x0, you get 2x0. 1, 0 goes to 2, 0, 2, 0 goes to 4, 0. This is also in U1. So here, T will be an operator on U1 if you restrict it to U1. So T restricted to U1 is an operator on U1. In other words, U1 is an invariant subspace of T. On the other hand, if you take T restricted to U2, if you plug in some 0y, what do you get? You get y, and this one is not in U2, right? So T is an operator, but if you restrict it to U2, it doesn't take vectors in U2 and map them back to U2. So U2 is not an invariant subspace. So in this example, we can see that you start with an operator. In general, if you take a subspace, it doesn't need to be invariant because it just maps things in the subspace to V, not necessarily back to the subspace. However, sometimes you can get an invariant subspace. In that case, the restriction is an operator, and that will be a nice thing. Okay, and hopefully, when you look at this picture, something that you can remember is the idea of an eigenvector. For this linear transformation T, what it does to E1 is it maps to 2E1. Stays in the space because it just scales it. So a one-dimensional invariant subspace of an operator should be related to the notion of an eigenspace. Okay, so I guess I will leave off here. And next time, on Monday, we will go through 5A, basically. All right.